Hello, my friend. This is another lecture related to the introduction to statistical geometry. In this lecture, we want to talk about the measure for the state of lines in the plane. Okay, let's do and follow together. In fact, intuition suggests that a reasonable measure for the number of the points in the closed region in the plane in the area within the closed region. Then what will be a reasonable measure of all possible lines cutting a closed convex curve like C in the plane? I will formulate the question for you exactly, and I will explain you what does it mean, what's the meaning of closed convex curve in the plane. So I mean, if all point on the line segments connecting to arbitrary point of the C are inside and or on C, then curve C is called a closed convex curve. Okay. First of all, let me formulate the question for you. What you want to say exactly and ask. Yeah, we are trying to find the answer of this question, and in fact, right now, I want to discuss about a little bit some concept and definition related to geometry. I mean, especially convex curve and closed convex curve, especially. Okay, definition one. First of all, we discuss about the definition of the convex curve. A convex curve is a simple curve in the Euclidean plane which lies completely on one side of each and every one of its tangent lines. Let me describe for you this concept by one figure. Okay, here we have one curve, and here stochastically it is closed, and let's suppose I make one tangent line here, and you can see that all of the curve, it would be in the one side of this tangent line. Also, it would be like this if we consider that. Let me change the slope of this line. It would be like this also. Okay. So, also if I consider the one non-closed curve, let me also do that and discuss about that with you. Right now we have another curve, and this curve is not a closed, it's like open board. And let me move my line. We have a one tangent line, something like that at this point, for example. At this point, and you can see that all of the part of the, and if you continue this line, I mean, you can see that all of the part of the curve, it would be in the left hand side of this line, in this tangent line. Okay, but let me show you one non-convex curve, I mean concave curve. Okay, let me just a moment. Okay, we have this curve, and it is simple curve. I mean, the simple curve is not cutting itself or crossing within itself, but right now we want to draw the tangent line at this point. Okay, you have this line. Let me, oops. Okay, and here you have seen some part of this curve. It is this side, okay, and some part of that is this side. So this is not the convex curve. Okay, Let's discuss about another definition. Okay, we say that a convex curve is closed, and actually we already considered it is a simple curve if it divides the plane into regions, free regions, inside, outside, and on. Let's suppose we have, for example, it doesn't need to discuss about this too much, but for example, let's have, oops, sorry, we have this, it is closed, and you can see that it's 1, 2 inside of that, and 3 on it, inside of it, and outside. That's it. Okay, but we have a different definition about convex curve that let's discuss about that a little bit. Let's discuss another form of definition of convex curve. Let's for one moment eliminate and about the word of the curve. Close, sorry. Closed curve we define as the boundary of a convex set in the Euclidean plane. Let me show you by the picture. Let's consider that figure we have in the left-hand side, okay? And this is a convex shape or convex set. So it means if you consider each 2 points and connect them like one segment, it would be again inside of the roughly inside of the object. Right now, let's eliminate inside of that. The purple color, and only we consider the boundary of that. So we have this in the right hand side. So we can say that this shape, it would be a convex curve. It would be another definition of the convex curve based on the convex set. Okay, right now we come back to our main question. Take any directional line through O and draw parallel line at delta rho units apart. The distance between this line should be equal to delta rho. Let me draw in the picture. Okay. More cleanly. I don't like. Okay. This part should be equal delta rho. So consider the extreme tangential Okay, let O be a point inside a closed convex curve C, this shape, and take any directional line through O, okay? And draw parallel lines at rho, delta rho unit apart. The distance between these two parallel lines should be equal to delta rho, and consider the extreme tangential lines in this set. You can see in the first picture. Assume that delta rho is sufficiently small. Okay, and let S1 be perpendicular from O to tangential line. I mean, these lines and this line. So let the length of OS, I mean this guy, should be equal to rho. Okay, if delta rho is taken as a one unit, then the number of parallel lines from O to S, you can see in the picture, is equal to length of OS, which is rho. What does it mean? It means if we consider this is L1, this is L2, and this is, for example, LK, K which is equal to rho. Okay, hence a reasonable measure for the number of parallel lines in this figure is the length S1. Okay, so now consider a rotation of these parallel lines through a small angle rho theta, like this. You can see that. Yeah, like right now we are using some concept related to infinitesimal transformation, something like that. And now SO S1 has changed to TO T1. You can see in the second picture. If rho is treated as a function of theta, it means rho is equal to rho theta. So we can say that infinitesimal change in the number of the line is infinitesimal number of line is equal to rho theta d theta. So the total number of the line is available when theta goes for a full rotation, or by the integral for theta goes from 0 to 2 pi. Okay, so I mean, let me write that. The total number of line integration from 0 to pi for this function rho theta d theta. So we can look at this problem. We discussed about this already. I mean, the invariant measure for a random line G in the plane in the term of the rho is proportional to d rho d theta. And taking the constant of proportionality as a unitary or considering the normalized measure, one has, we discussed about this already before, I mean dg, which is equal to d rho d theta, where dg is often called element of density, is element of density sets of lines. So this density can be written in terms of the parameters in the values representation of the line G. Some of these are given as an exercise at the end of our lecture. Thus, the integral over this density for the event that the random line cuts C is the measure for the set of the line cutting C. Note also that the effect of the rotation throughout delta T is that the tangential point A is now moved to B. And under a full rotation, A passes through every point on C. For delta theta goes to 0. If the length of the arc from A to B, denotes by delta L, like here, then the total number of the line cuttings and the convex curve C can also be measured by adding up such delta L. And we have the following result. Right now I formulate the theorem related to this question, and we want to answer to this question formally and officially. Okay, let's do it together. Okay, right now we have theorem 14. A measure for the set of lines cutting a convex curve like C is given by this formula, and integral of dg, it is equal to integral of d rho d theta, and integration from 0 delta, which is equal to 0 to 2 pi rho theta dt d theta, which is equal to this curve integration dl, which is equal to n, where L is a parameter of C. Okay, sounds cool. Okay, right, I want to talk a little bit about expected length. Let's suppose the line, this line, x cosine theta plus 1 sine theta is equal to rho, cut the domain D in this guy, and make an intercept of length L as shown in the figure. You can see, this part, it is equal to, let me show you the picture, this guy. Okay, so then for a fixed theta, okay, from 0 to pi, theta from 0 to pi, and 0 is the element of the area in D. Okay, so thus for 0, for theta in this interval and fixed, we can say that, let me write that, for theta in this interval and fixed, can say that integration L d rho, which is equal to A, where A is the area of this guy, is equal to D. So hence we have another way to drive in the result I mean, one of the previous results, and we can formulate one theorem. Let me formulate for you in the next page and discuss it together. Okay, let's formulate theorem 15 together for a random line in the plane not passing through the origin, cutting a closed domain B up with area A and making an intersect with this domain B. We have this relation. I will show you the connection of that with previous theorems, not previous one. And the expected length of, or the mean length of the chord I can be taken as PA over, the parameter of L, where L is a parameter of L and dg is the differential of G, is the element of the invariant normalized measure for the line. Just a minute. Let me bring previous and that theorem as I promised to you. We already discussed about the theorem 13, and right now we want to only inherit theorem 13 prime from that and make a connection between theorem 13 prime with this theorem, theorem 50. Okay, let's read the theorem 13 prime. An invariant measure if all lines in the space intersecting a plane region W of with area A is given by this integration. We know that this formula, and we find already the density function in the theory 13. Right now we want to use that, and if we calculate this integration, finally we have which is equal to this integration, which is equal to, in fact, pi over 4, and finally it is equal to pi a. And right now I want to make a connection and compare these two theorems together. Just a moment. Okay, right now you can compare these theorems together, and in fact we are finding this result in the two ways. It's very good to compare them and understand the difference, and learning different methods actually for solving problem, it would be useful and help you in the future. Okay, before I mention new theorem, let me discuss about one concept related to differential geometry. I want to talk about piecewise and differentiable curve. Okay, what is the meaning of this concept? Okay, we have this definition. A piecewise differentiable curve is a mapping from this closed interval to M of a closed interval, the closed interval AB in the as a subset of the real number into M and satisfy the following condition. There exists a partition of this interval like this, such that the restriction of C in each closed subset, like Ti plus one part of this partition, are differential. Okay, right now we want to discuss about one new theorem and new results. Okay, right now we want to discuss about Grafton formula and discuss about one interesting result. Let's suppose a piecewise differentiable curve in the plane which has a finite length. I mean, let me write that. A piecewise differentiable curve, PDC, is a stand for piecewise differentiable curve in the plane which has a finite length, length L can be described by a parametric equation like this: x is equal to x s and y is equal to y s. And here s is the arc length. Here s is the arc length. So suppose a line G intersects C at the point X and Y. Okay. Okay, suppose a line G, I mean green one, intersects C, I mean the yellow one, at the point X, Y, and consider the tangent, I mean this blue line, to the curve at XY, okay, blue one. If the line G makes an angle phi with this tangent line, then the line can be also determined by S and phi. Thus, one can see that, in fact, can say that if I can we move this guy here, okay. Right now, we can say that d of G, which is equal to d rho d theta, which is equal to absolute value of sine of phi d s d phi. In fact, where rho is a perpendicular distance of line G from the origin, and theta is the angle between perpendicular makes with the x-axis. Okay, it means this guy, this distance, perpendicular distance, origin, which is equal to rho. And if I continue, I mean, already this is line and it is possible to continue that, okay, till here, okay, and this angle, we say that this is theta. Okay, integrating over all lines that intersect C, we have double integration, absolute value of sine of phi ds d phi, which is equal to integration from 0 to L ds an integration from 0 to pi, absolute value sine of phi d phi. So, and let me a little bit change this guy because I need more space. Which is equal to 2 times L. Okay, I mean, here actually, what I did, here I integrate from double integration from dg, and each line has to be counted as many times as the number of intersection with C. If n is the number of intersection point with C, okay, let me little bit okay. If n is the, we can say that, let me write here, if n is the number of intersection points with curve C, then we can say that double integration all of dg, which is equal to 1 integration of n dg. So, and hence one obtains the celebrated Crafton's formula. Let's formulate as a one theorem, and we will discuss it. Okay, right now we have theorem 16. Let a random line G in the plane cut n times a piecewise differentiable curve of finite length L. Let dg be element of the invariant normalized measure for the line G. Then integration n times dg is equal to 2 times L. Let's discuss about a little as a simple illustration of this result. Okay. Result. Okay. If a line cut a closed convex curve in the plane, okay, let me write that. If a line cuts a closed convex curve, in the plane, then it cuts at 2 points. 2 points. So, or n, which is equal to 2. And we can say that, and okay, if we substitute in this formula, what we have, integration 2 times dg G, oops, 2 times dg, which is equal to 2L. Okay, right now we can cancel 2 from both sides. Then we can say that integration of dg, which is equal to L. What is that? What is that? What is that? Let me come back to previous theorems. This is exactly the result obtained in the theorem 14. That's it. Okay, right now we will discuss about one example and we will formulate that with based on one question. Okay, a random chord of the closed convex curve cutting another convex curve inside it. What is what we are looking for? Which question? If C1 is a closed convex curve of with parameter L1 and another convex closed convex curve like C2 with parameter L2, which is wholly inside of the C1, then what is the probability that a random chord of C1 also cut C2? Okay, we want to find and formulate answer of this question. Okay, since we have assigned the measure for the set of lines cutting C1 as L1 and that of C2 as L2, the required probability is the ratio of the measure of the set of lines cutting C1 and C2 to the measure for the set of lines cutting C1, and that is L2 or in fact L1. Okay, in the figure, I mean this guy and this guy, a rectangle and a line segment are given as a C2 respectively. The line segment can be looked upon as a degenerated rectangle. Hence, the probability that a random chord C1 cuts and the line segment of L1 lying inside C1 is 2L over L1. Okay, so L is the length of this segment. L is the length of this segment. So let's formulate the theorem related to this, and officially we discuss about these situations. So let's formulate our result as a theorem 17. The probability that a random chord of the closed convex curve C1 of the parameter L1 also cut a closed convex curve C2 of parameter L2 lying wholly inside of the C1. You can see that one of the cases is P, which is equal to L2 over L1. And if like this case, I mean for case 4, C1 is a line segment of length L, then is reduced to this case P, which is equal to 2L over L1. That's it. But let's discuss about another interesting example. Hey, in this example, we want to talk about random chord of the closed convex curve C1 cutting another closed convex curve C2 overlapping C1. Let's formulate this example as a one question and we'll try to answer all questions. Okay, our question is, what is my mistake, what is the probability that the random chord of C1 also cuts C2? We want to answer to this question. We have the two overlapping convex curve in the plane, like this picture, and let AB and DE be two common tangential lines to C1 and C2. Let me draw. Okay, one of them. Line. I have one line here. Wait. Okay. One of them would be like this. Let me. Okay. Another one would be like this. Okay, and let's copy one more because then they have two tangent lines. Okay, right now we can say that here as A and here as a point B and here as a point E and here as a point D. So let the parameter of the curve C1 and C2 be C1 be L1 and C2 be L2. So the parameter of this guy, we consider that L1, and the parameter of this guy, we consider it's L2. Then we know that from previous discussion, L1, which is equal to the measure of the set of line cutting C1. And C1, which is equal to the measure of the set of line cutting C1 alone, plus the measure of for the set of cutting C1 and C2. Okay, let me write that. Okay, I write for you L1, which is equal to measure for the set of line cutting C1. I mean, actually, the measure for the set of line cutting C1 only, plus the measure for the set of line cutting C1 and C2. For L2, we need to change the role of C1 to C2. That's it. It doesn't need to write anything more. So, but we can say that consider one convex body. I mean, this, I put some point in the figure. This convex body, we have one point F and one point here we have G, and here we have J, and here we have H, and here we have, for example, K, and here we have C. Okay, let's consider that the convex body F A B C D F, which is also called the outer cover of C1 and C2. This is outer cover of C1 and C2. Okay, and denote the parameter, a parameter of that, which is equal to, I mean, we have one shape like this. Parameter of that, which is equal to L1, L2. Okay, so what can we say that right now? Then L1, L2 is the measure of all line cutting at least one of the C1 and C2. So this is L1 and L2, which is equal to measure of all line, measure of all lines cutting at least one of the C1 and C2. So it means cutting either C1 alone or C2 alone or both C1 and C2. So hence the measure for the set of line cutting both C1 and C2 is like we are using principal inclusion and exclusion principle. Okay, so it would be like this. Let me draw this guy. I mean the final, it should be the measure for answer, it would be L1 plus L2 minus L1, L2. Okay, right now let's formulate our theorem. Okay. Okay, theorem 18. Let C1 and C2 be overlapping closed convex curves in a plane like this picture, and the probability P that a random chord of C1 also cuts C2 is P, which is equal to L1 plus L2 minus L1, L2 over L1, where L1 and L2 are parameters of C1 and C2 respectively, and L1, L12 is the outer cover of C1 and C2. Okay, I think for this lecture it was enough, and we'll continue in the next lectures. Okay, see you. Have a nice time.